Well, we're down to our last 2 weeks of academic instruction, and so I want to take a real quick little look at logarithms. But before we get to logarithms, let's talk about some rational exponents. And interesting, one of those four objects stayed there. I wonder what that means. We'll find out. So we want to be able to evaluate expressions with rational exponents. In other words, what happens when the exponent is a fraction? Now, this exponent table is available on Quick Schools. You can download it if you want. You probably don't need to print it, but you might want to be able to look at it. And I'll have some examples later on which kind of show how I would use this exponent table, right? So it's not a multiplication table, it's an exponent table. So again, what if I come up with, I don't know, like 512 raised to the 2/3 power, and let's pretend I want to try to tackle this without a calculator, right? Now, the bottom of the fraction is going to be the root, and then the top of the fraction is a power. So when I see the exponent of 2/3, the 3 says, hey, take the cube root, and then the 2 says, hey, raise it to the second power. So I'm thinking for 512, I can do 8 times 8 times 8. Notice that 8 times 8 times 8 makes 512, and it's 3 identical factors, which is what I need if I want the cube root. So since the bottom of that fraction on that exponent had a 3, I needed 3 numbers that were identical, right? So if I tried like 7 times 7 times 7, 343 would have been too small. If I tried 9 times 9 times 9, 729 would have been too large, right? So I can take the cube root, and that will leave me with an 8, right? So the cube root of 512 is plain old 8. Now I can square that. 8 times 8 is 64. Right? Notice that the exponent 2/3 is less than 1, and so the answer 64 is less than that number I started with, 512. Right? If the exponent is less than 1, my answer should be smaller than whatever number we had started with before we applied the exponent. Also note, we use 2 of the 3 equal factors. Right? That's what that exponent of 2/3 is telling me. Say, hey, you need 3 equal factors, use 2 of them. Okay, let's take a look at something else. What if I want 32 raised to the 7/5 power? Okay, the denominator is a 5, so I need 5 equal factors, right? And of course, in this case, it's going to be 2 times 2 times 2 times 2 times 2, right? Those are 5 equal factors. They multiply to make 32. So if I take the 5th root, I just have 2. Now the numerator of that exponent was a 7, so I need to take 7 2's, multiply them together, and get 128. Notice that the exponent 7/5 was greater than 1. So my final answer, 128, was greater than that number 32 that I started with. Right? If the exponent is more than 1, the result we get should be bigger than the original number. Also notice that we ended up using 7 of the 5 equal factors. Okay, now, what was that exponent table all about? Right? Some of us, these numbers just like dance in our heads, and some of us are like, oh, you're kidding me. What's going on here? So let's go back to that first example. I claimed that 512 to the 2/3 power was 64. So if I look at this exponent table, I can find the number 512 on it, and it's underneath the exponent of 3. Notice if I look off to the left, I'll say, oh, it was 8 to the third power made 512, right? That's where that 8 times 8 times 8 came from. And I say, oh, if I had that 512 underneath the exponent of 3, but I want to adjust it so I'm underneath the exponent of 2, notice I'm at 64. Should we look at the other one? 32 to the 7/5 power. I just claimed that the answer should have been 128. Okay, so again, I'm going to look for the number 32 on the exponent table, making sure I pick a 32 that's underneath the 5, right? Because I got to take a fifth root. And say, okay, so I'm going to find the number 32 underneath the exponent of 5, but now I want to adjust it so I'm underneath the exponent of 7, and sure enough, there's 128, right? 2 to the 5th power is 32, so when we took the 5th root, we got 2, but then 2 to the 7th power got 128. So as much as possible, we want to try to do this stuff by hand, and we want to show some step-by-step work like I just had on the previous slides. However, for some of us, you know, if we look at 512, we're never going to guess 8 times 8 times 8. And so that's what you can use this table for. You say, oh, I need the cube root of 512. Oh, it looks like it's going to be 8, right? 8 to the 3rd power is 512. And so this table could be very, very useful. If worst comes to worst, however, right, sometimes you're like, whoa, right? I tried to do it by hand. I looked at that table. I tried to use everything, and I'm stuck. Or maybe I think I did everything correctly, but how do I know if I got the right answer? So, again, let's pretend we've got this one, that 512 to 2/3 equals 64. And let's pretend I worked it out step by step on paper, or maybe I referred to that table, but I'm like, you know what, I'm not certain I've got the right answer. Okay, so if I get a calculator, here's a screenshot of a TI-84, and it uses the caret symbol for the exponent. Ah, the picture is from that very first slide. Caret is one of my favorite homonyms. Right, there aren't too many homonyms where you actually have 4 words that basically sound the same. These 4 words are pronounced almost exactly the same. Of course, you've got the caret that you eat, the carat that is the measurement of the purity of gold, right, where 24 karat would be pure gold. Then you have the carat, which is used in the weight of gemstones. And then you use the symbol carat. And for many calculators, they use that caret symbol for the exponent. Also notice that I've got parentheses on the exponent. If I don't put the parentheses on the exponent, instead the calculator will read this as, oh, take 512, square that, get a really huge number, and then take that really huge number and just divide it by 3. That's not what I want to have happen. So be careful about exponents. And then, of course, some calculators use like an X to the Y button. And that X to the Y button is what creates the exponent. I find this one kind of funny because the calculator I found had an X to the Y button, but then up in the display it still shows it as a caret. Oh! How about this? Something just exciting. We could have negative rational exponents. Right? So a positive exponent tells me how often I'm going to multiply. A negative exponent tells me how many times I'm going to divide. Right? Remember, division is just multiplying by the reciprocal. And so, as an example, 2 to the 4th power, you're like, oh, come on. 2 times 2 times 2 times 2 is 16. But if I saw 2 to the negative 4 power, instead of 2 times 2 times 2 times 2, I've got 1 divided by 2 times 2 times 2 times 2. So instead of 16, I get 1 over 16. Notice the answer is positive. The negative exponent does not make the number negative. The negative on the exponent just tells me that I need to do the reciprocal. So instead of 16, I end up with 1 over 16.
So, you want to talk about it with me?
Okay, so what to do, right? So instead of just seeing the top and bottom of the fraction of the exponent, I also have the negative. So I prefer to take this route. You can actually go in any order, but if you start by taking the power, you're going to get a humongous number, and then you're going to try later take the root of that. So I say, hey, no, let's just get rid of the negative. And so there's no more negative on the exponent. Instead, I've got the reciprocal. Right? That's all the negative tells me to do. Take whatever we had, put the whole thing underneath the number 1, so it's the bottom of the fraction now. Okay, take care of the root. I need a 4th root. So in my head, or with the exponent table, or if necessary, I could grab a calculator. I could figure out that the 4th root is 5. Right? If need be, you can even guess and check it. 2 to the 4th, 2 to the 4th power, 16, too small. 3 to the 4th power, 81, too small, right? Just guess and check with the calculator, and eventually you'll say, aha, it's 5 to the 4th power. That made the 625. So I took the 4th root. Now I can take care of the power. So 5 to the 3rd power, 125. Okay, new example, different example. Let's try this one instead. Okay, negative exponent. So that tells me that I've got to take that 343 to the 2/3 power, put it underneath the 1, so it's the denominator. Now I need the cube root. Let's see, 2 times 2 times 2 is 8, way too small. 10 times 10 times 10 is 1,000, way too big, right? So I'm somewhere between 2 and 10. Well, I should eventually figure out that 7 times 7 is 49. 49 times 7 is 343. So sure enough, 7 to the 3rd power made 343. So if I take the cube root, it goes all the way down to 7. You can check on that table and say, hey, if I look at 343, and I look and line it up underneath the exponent of 3, I can see that it was a base of 7, 7 to the 3rd power. Now, of course, I got to square it, and I see it's 49. And again, with that exponent table, you should be able to line these things up and say, oh yeah, the 343 is underneath the exponent of 3. It lines up with the 49, which is underneath the exponent of 2. Right? And so we got a groovy little worksheet here. Again, fire off an email if you're a little confused, want some assistance. I'm also available for Zoom chat, but for the most part, it seems like a quick email or two has been answering everybody's questions.